Okay, in this lecture I want to continue with linear regression, but let's now leave the Bayesian world and let's leave least squares and ridge regression, and let's think about some more things that we can do for the linear regression problem. So primarily in this lecture I want to discuss what can be called underdetermined linear equations. So in this case, again, we have the regression problem y is equal to or approximately equal to x times w. But the matrix x is fat, so it's n by d, and d is now potentially much greater than n. So we have many more dimensions than we have observations. And so this is called an underdetermined problem. Intuitively, you can think of it like this, where y is our response vector, and x is a short and wide matrix, and w is very long. So w is now very long, much longer than y. And so we have an infinite number of potential solutions. There are an infinite number of vectors, w, that can solve this type of a problem when the number of unknowns is greater than the number of equations. So these sorts of high-dimensional problems often come up in machine learning. For example, in gene analysis problems, there are often thousands of genes, but only hundreds of subjects. Images can have millions of pixels, but we might not have that many images. Even polynomial regression, which we've discussed previously, where the original dimensionality of the problem might be small, but we turn that into a polynomial function to increase its dimensionality, can quickly lead to this type of a scenario. So let's look at how we can do linear regression in this sort of a situation. So first I want to discuss something called minimum L2 regression. So this is not necessarily an algorithm that we'll perform or want to use, but it's something that I'm going to use as an excuse to introduce two different techniques that are very useful for machine learning. And I want to introduce these techniques in the context of a very simple problem. So one possible solution to the underdetermined problem that we're discussing in this lecture is called the least norm solution. So in that case, the vector w is equal to x transpose times the inverse of x transpose times y. Remember, the least square solution was x transpose x inverse times x transpose y. Now we've kind of flipped that solution. To see why that's a solution, it's very simple. Simply multiply the left side by x, and we'll realize that x times w ln is equal to y. And so therefore it is definitely a solution because this matrix product cancels out. So our goal is to show that among all possible solutions, this least norm solution has the smallest L2 norm. And so how can we do that? So to this end, what we can do is we can represent any other possible solution to this problem as the sum between the least norm solution and some vector in Rd that is in the null space of x. And so remember that a vector is in the null space of a matrix, which is what this is saying. A vector delta is in the null space of the matrix x if the product of x with that vector is equal to 0, and the vector has non-zero value in it. So we can write this new solution as the sum of the least norm solution plus some vector delta in the null space of x. And so if we then want to show that that is a solution, it's very straightforward. What we can do is take the product of the matrix with this new solution vector, which I write as a sum. Then using simple algebra, we can show that that's equal to the product of x with the least norm solution and plus the product of x and delta. And since this is equal to 0 and this is equal to y, the new solution that we found is also a solution to the problem. So in fact, there's an infinite number of these potential deltas that we can pick because the dimensionality of the problem is much greater than the number of observations. So what we're going to show is that this least norm solution, what I'm calling the least norm solution, is the solution for the vector W that has the smallest L2 norm. And so the proof of this, I'm going to show two very simple proofs, are going to introduce two general concepts that are often used in machine learning, which I mentioned previously.